Okay. Yeah. Thank you very much to you and the organizers for giving me the possibility to present my results. In this talk, I would like to discuss the use of especially my research of quantum Monte Carlo, and especially fixed and node diffusion Monte Carlo, for investigating material modeling, especially in the cases where we need high accuracy. So, okay, no, yeah. Okay, so I mean, we need the quantum Monte Carlo accuracy. Well, not all the time, because very often we can use density functional theory, and this is enough. But there are systems where the density functional theory is not able to give the right accuracy, and in that case, it is worth to spend do more expensive simulation using quantum Monte Carlo. And so I would like just to give the flavor of like when it is needed, and what are the implications of not having the right accuracy, taking these simple examples, which is the case of a water molecule adsorbed on the graphene sheet. If I go to see the interaction energy of the water with the graphene sheet at the different distances from the graphene sheet, what I obtain is a curve that will have a minimum, and the minimum is the absorption energy. And depending on the method that I use, I will obtain different curves. So here in this plot, we see the interaction energy as a function of the distance as obtained for different approaches, different flavors of density functional theory. And I don't put the label to the colors, just because the idea that I want to show here is that the flavor of density functional theory, that it changes a lot, and essentially you can have all the possible results from no interaction to an interaction that is of the order of roughly 160 millielectron volt. Okay. And even if I go to methods that are considered like benchmark, so either like those flavor of density functional theory that we think they are trustable because maybe they have van der Waals correction, or we try to mix with a couple cluster and benchmark them in a smaller version of the system, we still remain with an uncertainty that goes roughly from -70 to -130 millieV. And so the question is, okay, do we need to be more accurate than this, or this is enough for our purposes? It seems it's not a large interval, because it's just roughly like a little bit more than 1 kilocal per mole, which is considered the chemical accuracy. However, if I then, do molecular dynamic simulation of not one, but many water molecules over a graphene sheet, and I see how they behave in my simulation if I consider their molecular dynamics, then depending on like if I have an interaction where the interaction energy is of the order of 70 millieV, I end up having the waters forming a droplet like this with a contact angle of around 90. If it is 130, then waters totally absorbs on graphene. So in this apparently little interval, I see essentially that I have a physics that is might be totally wrong. So also this little uncertainty matters. And okay, when I do material modeling, just want to give the idea, like there are many approaches. that I can use, there is density functional theory that is the working horse, is the first one that people try. If I have to simulate very large systems, I might go to force fields, which are orders of magnitude faster, but also the accuracy is not always very good, or I can even go to Gauss-Green models. Here we care mostly when we are not happy with the density functional theory, and so we go to wave function-based methods, which are 3 or 4 orders of magnitude more expensive than density functional theory, but they can be more accurate. And in these approaches, the mostly used are quantum Monte Carlo if the systems are large, or couple cluster with single, doubles, and perturbative triples excitations for systems that are not that large. Okay. Well, just to finish the story on the water graphene, we studied the water graphene system with diffusion Monte Carlo for 3 different orientation of the water molecule, and obtain these curves. And so we have yet another result. And in this case, where the experiments cannot tell what was the actual interaction with high precision, what we did to be confident of our results was to ask some collaborators to do also the reference method calculations. And so Andreas Gruneis made this periodic couple cluster calculation, which are given the interaction that you see with the black square. And Georg Kresse made RPA with a single with the GW single energy corrections, obtaining the results, the curves that here is in Chan, and here, so there is a very good agreement among these approaches, and we are confident that so we have a quite accurate estimation of this interaction. And then we have a look at the past works on this system, which were different from our estimations, but I mean, our calculations could help to understand some of the weaknesses of the previous calculations that might be having used 2 small basis sets for quantum chemistry calculations, or relying on extrapolations on smaller systems, but where they didn't go to something large enough for having the extrapolation to be trustable, and so on. So, okay, in this system we see consensus among reference methods. Another system where is quite interesting for material modeling is the prototypical molecule surface system, CO absorbed on MgO surface, the 001 surface, which is a system that has been already also quite studied, both with theory and experiments. Here, the gray triangles represent the experimental values obtained mostly from temperature program distortion experiments. And as you can see, they do not give the consensus among these different evaluations is not good. And then there are some results from the simulations, which are here represented in with crosses or with circles, depending on if they are from a cluster approach, because the system is a surface, so it would be infinite, or with periodic boundary conditions. And yeah, you can see there is no agreement. Recently, Benjamin Shi, who is a PhD student in Cambridge, which I co-supervise, studied this system with quantum Monte Carlo, with the fixed node diffusion Monte Carlo in particular, using periodic boundary condition, and there is this number here. And also he studied it with a couple cluster using a cluster method that he also developed, obtained this other number in red. And then our collaborator, Andreas Grunes, made an evaluation using periodic couple cluster, obtaining this other method. And so again, we see a very good agreement between the experiment, our simulations, so with diffusion Monte Carlo and couple cluster approaches. Moreover, Benjamin also reconsidered the experiments, the previous experiments, and give an improved experimental estimation. So, okay, I don't want to go into detail on the couple cluster approach, but this was discussed in this previous paper. And essentially, the idea is to go through doing couple cluster calculation of systems cluster of increasing size and then doing an extrapolation to the bulk limit. The concerning is that the point about the reconsidering the experiments, one have to consider that the value that is obtained from the experiments is not exactly the assertion energy, but an energy that has to be corrected for the 0-point energy, thermal contribution, and other terms. And the most important thing that we saw is that there is a pre-exponential number that is applied. And these three experiments, for instance, they didn't use the same pre-exponential number. So if you try to see which would be this pre-exponential number that make the results to be more in agreement with our simulations, and you apply the same number to the three of them, they move to the new values that you see here that are indeed in agreement with our theoretical estimation. So in this other system, again, about assertion on a surface, we see good agreement between reference methods and also with the experiments in this case. We, in the past, studied molecular crystals, and in particular the lattice energy, so the energy of a molecule that is in a crystal compared to the gas phase. For a set of interesting molecular crystals, and for which there are experimental estimations. And so we compare the experimental estimations with our prediction from simulations. And in this plot, we see the 8 molecular crystals under consideration. And in the y-axis, we have the difference between the experimental estimation of the lattice energy and the computed lattice energy. So we would like it to be 0. But I mean, there is some experimental uncertainty that we have estimated here to be roughly plus or minus 1 kilocal per mole, so roughly 4 kilojoule per mole in gray. And as you see, the numbers obtained from diffusion Monte Carlo, which are in green, dark or light green here, they are always within the uncertainty. So we are quite happy of the results. From the literature, we collected also couple cluster numbers, which are not available for all the crystals because some are too large for couple cluster because the scaling is quite bad with the system size. But where it is available, we also have a good agreement. MP2 and RPA, they are not so good, but RPA with GW single energy correction, they are quite good. I mean. And more recently, we consider more in detail one of the most interesting molecular crystals that you can have, which is the case of water. So the ice phase diagram. From the experiments, we know that the phase diagram is this one that you see here on the left, where we see like there is a liquid phase, and then for low temperature, there are a lot of different polymorphs. So like water rearranged in different, with different orientations. And depending on the temperature and pressure, the more stable polymorph is different, and there are all these phase transitions. So we might ask, okay, can we predict with simulations such a complicated phase diagram? And there's been recently two works that try to do that by using density functional theory and machine learning. So I'm going first to discuss a little bit the previous works. In this work, this PRL of 2021, essentially, if in gray we see the phase diagram from the experiments in gray, in red instead we see what was their prediction using density functional calculation from scan and machine learning. And we see that there is a qualitatively quite reasonable agreement, although like the phase transitions, they are not happening at the same temperature and pressures. The main issues that we can observe is that there are some phases that are missing. In particular, there is a phase 3 that is not observed at all. And if one tries to see the phase transition with one of the mostly used force field potential, which is tip4p, we have that actually tip4p would have the phase 3. Although like even this phase diagram is not perfect. And so okay, this is one work. The other work here uses again density functional theory with different setups, PB0, D3, B3lib, B3, and so on, plus machine learning, and predict the different phase diagram like you see in the figure in the middle and on the right in here, to be compared with the experimental phase diagram. And even here there is not the phase 3, and the phase is I mean, like qualitatively that's not too bad, but quantitatively the phase diagram is not very good. And so we decided to try to do some investigation of the phase diagram of ice ourselves. In particular, most of the calculations here were made by Flaviano Della Pia, who is a PhD student in Cambridge, which I'm co-supervising together with Dario Alfè and Angelos Michailidis. Flaviano selected a set of 13 polymorphs of ice to represent the overall phase diagram. And then he performed diffusion Monte Carlo calculations. He considered the relative lattice energy, which is the quantity that would tell which is more stable than the others, and so determine the phase diagram, and compare it with the experiments. And we have a quite good agreement between the diffusion Monte Carlo and the experimental values, especially if we take into consideration that here in the experiment there are small error bars, but actually this is under the assumption that the 0-point motion is just the same for all the polymorphs. But if one instead try to compute them, and they seems to me not the same. So the error bars are indeed larger. So considering this uncertainty in the experiments, our DMC result seems to be quite good. And okay, this result can of course be used to benchmark density functional theory and see which one is to be trusted the most. But can we say something on the phase diagram? So, I mean, doing a proper evaluation of the phase diagram would imply a lot of expensive calculation. But if we try to, I mean, introduce some approximation, we could say that maybe temperature effects can be considered to contribute roughly the same between the ICE5 and ICE3. Then we should notice that well, we don't have ICE5 in the dataset because it's the disorder version, but there is the order version that is ICE13. And okay, and again, we consider that 0-point energy contribution is roughly the same. And to understand if the ICE3 would be stable, one should correlate the energy difference with the volume per water difference. And so we made that, and this led us to predict that there should be a phase transition at roughly half gigapascal here. So according to our calculation and with the approximation that we introduced, we could say that there should be a phase 3 if one does the diffusion Monte Carlo phase diagram. Why they didn't see that in the previous two works? Well, if we go to see the density functional theory functional that they used, they are indeed that the difference between the ICE13 and the ICE3 as the wrong sign, meaning that it cannot be stable because it predicts the energy of the wrong ICE to be more stable. Okay, so that was the reason. So it seemed that the energetics here is the main thing to have a more reliable phase diagram. Okay, and so in all these previous examples that I show, we essentially had that the agreement between diffusion Monte Carlo and couple cluster or with experiment was very good. And usually in the estimation of interaction energies for weak interaction, non-covalent interaction like those that we are considering, we are keen to think that DMC, diffusion Monte Carlo, fixed node diffusion Monte Carlo, and couple cluster, they are quite equivalent. And so we can just use couple cluster in small systems and diffusion Monte Carlo in large system because of the scaling. However, recently, we discovered that there are at least some systems where this thing seems to be not the case. And I mean, I'm referring to this work where I was involved, but the main calculation were done by Yasmin Aldani and Peter Nagy. And while in many systems there are agreements between couple cluster and DMC, there are some where there is a very big disagreement. And this disagreement is quite large, so it would make big differences for the chemistry. And if we try to see in which system of these disagreement, we notice that they are here, these ones that I have highlighted, which seems to be system with the pi-pi interactions. And this raises a question. So in these cases, which method is to be trusted? Is fixed node DMC or couple cluster? And okay, because we know both of the approaches have the weaknesses, so it's not straightforward to say, okay, we just trust this one. So I've been trying to focus a little bit on this question, but first I just want to give a brief introduction. I mean, a few slides about DMC. In this talk, I think that everybody knows the DMC, so let me remind that it is branching-based diffusion process that is used to project out the exact ground state from a trial wave function. And so after an equilibration time, we do just sample stochastically and have an estimation of the energy. The cost is proportional to the inverse of the imaginary time step. And I mean, the features of fixed node DMC are that it improves the density functional theory. The scaling is n to the third, and it goes well on ICP facilities. And in these large calculations, I always use a single Slater-Jastrow wave function because otherwise, I mean, it becomes very expensive and also difficult to control the uncertainty in the optimization. The main approximations are the fixed node or fixed phase approximation because we need to keep the system fermionic, the employment of pseudo potential, finite time step, modification to the green function to enhance stability, and in periodic system finite size errors. And typically, so how bad are the approximations? Generally, fixed node and pseudo potentials, they are considered to be not impactful because we benefit for almost perfect error cancellation in these weak binding systems, and all the other approximation can be checked. But it might be that in this system that we consider here, this point is not the case. So, okay, the main challenge in the large system is to keep the uncertainty small, and so to not be killed by the optimization. So I have done a few works in the past to try to make DMC more feasible for this kind of non-covalent interactions evaluations. And the last of these works has to do with the reproducibility and the use of pseudo potential. So I would like to briefly mention this. If we have all electrons, we have simply the Hamiltonian is simply a kinetic and a local potential. But when there are effective pure potential, there is also non-local potential terms in the Hamiltonian, and they introduce some an additional difficulty, like because in the time evolution there is one term that cannot be easily obtained, and even if we formulate in terms of green function, we essentially have the green function for the kinetic plus local potential part and the green function for the non-local part. But this one might give negative transitions, so it cannot be interpreted like a probability transition. So on top of the fixed node approximation, there is the need to introduce another approximation to deal with the non-local terms. The one that was introduced first was locality approximation, which were essentially one localize the non-local terms on the trial wave function. The other possibility introduced in 2005 is the T-move. And more recently, we suggested to use a yet different thing, which is to localize using only the determinant part of wave function and not the Jastrow, because in this way we essentially, if we obtain the determinant from deterministic methods, we are not affected by the optimization noise of the Jastrow. Okay, I skip a little bit of details, but essentially what we want to have is that independently of the Jastrow parameterization, we would like that, like if we have the same determinant with this scheme, we have the same diffusion Monte Carlo energy, at least in the limit of infinitesimal time step. And okay, so for this, in a system like this, where like this is an example where I'm showing the binding energy of a water molecule with benzene with the benzene molecule, and if I take a good Jastrow, well optimized Jastrow, I obtain essentially always the same binding energy with the locality approximation, with T-move, or with DLA. And these are in agreement with the couple cluster prediction, which is here in black. However, if my Jastrow is not optimal, which in this case, I mean, I made on purpose bad, but not that bad that you can see something wrong in the variance, but like it was not optimal. It was just a Jastrow for a slightly more far away water from benzene. What we get is that the estimation of the binding energy from locality approximation from T-move is totally wrong. You see, it goes here for the T-move, here for the locality approximation. With this determinant locality approximation, we just get the same thing that we would have for the good Jastrow. Okay, the result in green, and this is something that we think it is good for reproducibility, especially in view of the fact that the Jastrow factor have different parameterization, essentially in all the QMC codes. So it also helps to compare among different codes. And connected with the idea of comparing different codes, actually, I'm working on a comparison between 11 different codes on the prediction of these interaction energies. This is something that started with Sandro Sorella and Dario Orfei. We were comparing Casino, QMCPACK, and Turbo RVB results in order to see if we were getting the same numbers. But then I thought it would have been good to generalize the problem to all the community, and so I got the main developers of many other codes and asked them to do their own calculations. We defined the ansatz, the geometry, pseudopotential, basic set, and determinant, and we try to see if we can converge on the same results. This is a work in progress, so it's not yet finished, but so far I had a lot of results with from all the codes. Here you see, for instance, the total energy of water, and with the different kind of approximation for the pseudopotentials. And this is the evaluation of the binding energy. I'm not putting the labels because I'm still doing the analysis, and I didn't ask to everybody to publicly show the results, but I can show the results that I made myself, which are those with the Casino, QMCPACK, and Turbo RVB, which are here in green, blue, and red, and we see that we have a quite good agreement. for the T-move and the DLA approximation. We don't have QMCPACK and turbo RVP results for the locality approximation because essentially it is not stable, the simulation, so I couldn't do the calculations. Although I noticed that it would be stable with the compressed version of the code, but then the time step dependence would be slightly different for the other schemes. And I didn't report the determinant locality T-move, which would be doing the T-move, but within the determinant locality approximation. I didn't report because in principle, one can set in the QMCPACK the calculation to do DLA with the T-moves, but this setup fails a sanity check that I made. So the sanity check would be to see if the extrapolated energy, if I use or don't use the JASTRO, is the same. It should be the same because that was the purpose of the method. And in DLA, it is the same. Here, the QMCPACK results are these in light blue. But it is, so this is good, but it is not in the DLT move. So I think I'm not sure, but like it is not doing the meant scheme, so that's why I didn't report that. Okay, but okay, going back then to how we can improve our estimation of the pi interaction and see if we should trust more fixed node DMC or couple cluster. Well, what I did, the way I tried to tackle this problem was to inspect the weaknesses of fixed node DMC, with the idea that if I check all the possible issues I will find what goes wrong, and if everything works, then maybe we should trust the DMC. So I made the list of what I think might be weaknesses. One is bugs in the code, which I think it is not the reason, because we have two independent prediction from two different codes. There is the paper that I mentioned, but like in the same time, same period also, there were other calculations made by QMCPACK, by Anwar Benali and workers, and they essentially give the same numbers. I don't think it's at the pseudo potential because Anwar calculations are with all electrons. Then it might be that there is an issue with the optimization adjuster because they are large system and they can give a bias. But we made some tests. So we made calculation with the locality approximation, T-move and DLA, and we always got the same numbers. So I don't think it is the JASTRO. And it might be the way the determinant in the Slater JASTRO ansatz is initialized. But it seems to be not, because we also tried LDA, PB, PB0 to obtain the determinant, and we always got the same number. So the last thing would be if we need to go beyond to improve the fixed node, so the fixed node approximation, if we need to go beyond the single Slater determinant. And this thing is the last thing I would like to show, where I've been trying to go. So, okay, you know the trial wave function that gives the nodal constraint is a product of the determinant and the JASTRO. And in all the calculation that I showed, my determinant part was a single Slater determinant obtained from density functional theory. It might be obtained also for RT-Fock, but density functional theory works better. And one takes the orbitals, the occupied orbitals, to build the Slater determinant. The JASTRO factor instead, well, I guess everybody knows what it is. The point is the JASTRO factor is not changing the nodal surface. So I thought maybe one can think about a generalization of the Jastrow factor which allows to do large systems. Have not many parameters to optimize, but is still able to go beyond the Slater determinant. And so I had an idea that I share with Sandro Sorella, who was the guy who teach me to do QMC. And the idea was to use his code, Turbo R4B, to use a generalized ansatz, the AGP, which generalizes the single Slater determinant. It contains the single Slater determinant as a special case, and it is essentially implicitly multi-determinant. So the AGP contains the single Slater determinant and also a class of excitations that are called that are zero seniority excitations, which have a coefficients which are given from some coefficient lambda that are indeed what we can optimize. So this AGP indeed works pretty well. We have seen that in the past in cases where there is a strong correlation. For instance, in the evaluation of the twist energy of this molecule, ethylene, because when the molecule is twisted, we have the HOMO-LUMO energies that becomes degenerate, and so it is not possible to, one cannot describe this system with a single Slater determinant. And this case is something where also couple cluster fails, while with the single Slater determinant fails both at the variation and at the fixed node level, and also couple cluster fails, but DMC and fixed node DMC at the JGP with the RGP answers, they work well. They match the multi-reference couple quantum chemistry calculations, and so that's why we think it might be an improvement. So what we did was then to realize that we, however, needs to have good virtual orbitals. And so instead of using the molecular orbitals, we did natural orbitals obtained from MP2 calculations. And we consider a set of molecules, mostly of carbons, of increasing size, and applied our scheme and obtain these energies, which this is the energy gain with respect to the single Slater determinant. And essentially, we can systematically improve over the single Slater. Okay, we are trying to finalize this work, but I mean, that might be the way to go beyond single Slater determinants for the application that I mentioned. And okay, I think I used all my time. So let me just finally thank all the other persons which helped me with or contributed to the work that I presented.